In this lesson, I will be talking about number systems and how they're used in computers. So to get started, we'll talk about the number system we're all familiar with every day, the decimal system. But we need to go back to the history of it really, and you put yourself in the position, I suppose, of the first person who thought of these numbers and what they were thinking at the time. So just think about this for a second. The person who invented the numbers invented this symbol for 0, this symbol for 1, a different symbol for 2, etc., a different squiggle for 3 and 4, and all the way down to 9. And then the person decided to just go 1 0 after that for 10. Now we have to really think about this. Why did a person decide at 9 to go 1 0? Why is that the cutoff point? And it's something we often overlook. The reason is simply because we have 10 fingers. So you can imagine the first person who invented counting. He said, okay, that's 0 fingers, that's 1 finger, holding up 1 finger, holding up 2. So he was counting on his fingers. And then when he got to 9, he realized his 2 hands were full. So he went on and taught something like this. Well, now I'm back to 1 full hand. That's what the 1 means, and 0 fingers again. So in the place system, as we call it, that extra 1 now stands for 1 full hand, or 1 full set of hands. And he starts off again, then he's 1 full hand, and start off with 1 finger again. 1 full hand and 2 is 12, and so on. So that's the way it was done. That's how it originated at the decimal counting system. So now we can use that as a base for working out other number systems. And I want you to imagine there was some alien from some other planet who had evolved to have 8 fingers instead of 10 like humans have. And how would that alien count, do you think, if he just randomly ended up with 8 fingers, or 4 in each hand, or something like that? So that person might start counting like this: 0, 1, 2, 3, 4, 5, 6, 7. Now you realize he's getting to a full set of hands. So now it's 1 full set of hands and starts off at 0 again. 1 and 1, 1 and 2, etc. So we would call that the octal system because it's based on 8 fingers, whereas decimal is based on 10 fingers. So there's absolutely no reason why that alien civilization couldn't just use this method of counting all the time. And they would get fairly used to it in no time at all, just like we got used to counting to 10. So that's what's called the octal system. Now, I want you to think further. Now imagine an even more unusual case where the alien has just 1 finger, just 1 hand, there's not even 2 hands, 1 finger, and that's it. So then you'd count like this maybe. So 0 fingers, then hold up the 1 finger, that's 1 finger, and that's the hand already full. So now you come to 1 full hand and no fingers again. So that's 1 0 is the next number. And then you hold up your finger. So now you've got 1 full hand and 1 finger. Now you've got 2 full hands, so you open up the third one. So the third number 1 stands for we've now got 2 hands full, and we're starting off from 0 again. And you count up like that, and so on. So you realize that's a very strange looking system because it's only based on the digits 0 and 1. Every single number you can ever think of is based on the digits 0 and 1. And that's called the binary system. And if we go down through the binary system, we'll see here I've a lot of them worked out, and you might notice certain patterns after a while compared to the digital system. You see the hands get full fairly quickly. If you've only got 1 hand or 1 finger on 1 hand, the hands get full pretty quickly. So the number of hands goes up. So it goes across the digits much quicker than the decimal system, which takes a while to fill up 1 hand. So you can see the numbers get wider much quicker basically than the decimals. So if I go down along here, you'll see how it gets much wider. Okay, so back up again. Now it turns out that there is no alien, as far as we know, that counts in binary with just 1 finger. But if there is a machine that counts like that, as a matter of fact, the whole machine is based on this method of counting. It does nothing else, and that machine is called a computer. This is actually how computers count internally. Whatever you do yourself externally in decimal or whatever, it's always converted to a binary at some stage, and computers count like this. So why do they count like this? Well, if we go on to this next page here, which I call switches, you want to see it here. If you can imagine microscopic switches, and that's what they are, they're made of electronic components called transistors, but let's picture them as switches for the moment. So in a computer, At the smallest level, you've got banks of switches here, as they're called. So this is a bank of 8 switches. So there's 8 switches on at the moment, or well, they could be on or off. It doesn't really say there. Uh, and we call a bank of switches 1 byte, B-Y-T-E. So eight switches is 1 byte, and one switch is a bit. So the word bit in computers, 1 bit is a switch, 8 switches is a byte. So that's the first thing. Now, what's this got to do with binary? Well, if you look at the binary numbers here now, 0. A switch is either on or off. And that corresponds perfectly to binary, because in binary, you can only use the digit 0 or 1. There is no other digit you can use. So in binary, if you want, we'll say, to store the digit 0 on a computer, what the computer does is it just turns off all those 8 switches, and that's interpreted by the computer as 0 being stored there. It stores it by turning off all the switches. Now, if you want to store the number 1, well, that's just 1 in binary. So there's the number 1 there. That means the switch is on. The first switch, the first finger is on, but all the other hands are turned off. There's no other hand counted at the moment. Then you go on to 1-0. That means the first finger is off, or is down, and there's one hand full, so that switch is on. So 1-0 corresponds to on off, and all these others are still at 0, and so on. And you can keep going down like that through all the numbers, counting up in binary, and it turns out that every binary has a corresponding set of switches that are on or off. And that's basically how a computer works. It stores everything in switches that are on or off. And that could be the computer's memory or the computer's hard drive, or whatever it happens to be. So that's the system it uses. And we go on through another few there just to show you how big it gets, I suppose, towards the end. So you can see there, if you get down to a number like, we'll say 111111, that corresponds to, that's 5 1, so that's 5 switches turned on, and the first 3 are still turned off until you need them for bigger numbers. One more, 100 100 in binary is off off on, off off on, off off. So this is the first 100, 1 0 0. This is the second 100, 1 0 0, and these two are off because we don't need them yet. So that's how everything is stored. And now it turns out that every number has a code as well, and every letter in the alphabet. If you go to this there's a code called the ASCII code, which is recognized internationally. So if you go down through this, it turns out that every binary number, or every configuration of switches, has a corresponding number or letter. So if you go down here a bit, we'll see this ASCII code, as it's called. If you go down here, so there you see it starts at around, if you go across here, this is the equivalent decimal number, around 48, which is this in binary. And if you go across, that corresponds to 0. So that's how you store 0 on a computer. How do you store number 1? Well, number 1 is stored like this, etc. How do you store anything else? So the capital letter A, for example, is this code here. So to store the capital letter A in your computer, you'd have the first switch is on, the last switch is on, but all the middle ones there are off. And every little symbol in between as well, the question mark, the greater than sign, etc. And every single letter, everything you can think of that you need to type on a keyboard is stored in the same way. So that's called the ASCII code. Now, back to our first screen, one last set of numbers to talk about, I suppose, in the number systems. We talked about decimal, which is 10 fingers. We talked about octal, which is 8 fingers. We talked about binary, which is 1 finger. So it's just a 0 or a 1. There's also a hexadecimal code. So you have to imagine now the opposite situation. Imagine an alien with 16 fingers. So how would he count? Well, he'd start 0, 1, 2, 3, 4, etc. Now when he gets to 9, there's no need to go to 1 0, because there isn't a full hand yet. So he needs to invent new squiggles, I suppose, or new characters for the next few numbers. So what we've decided to do is, in this hexadecimal system, we've just started using the capital letters A, B, C, D, E. So 8, 9, 10, 11, 12, 13, 14, 15 is F. And now we have a full hand because it's 16 fingers altogether. So finally, after F, there's a full hand. So that's now 1 0 again, 1 1 1 2. So that's called the hexadecimal system. Now, why is the hexadecimal system important? Well, that's used in computers an awful lot, because if you correspond it to the binary system side by side, you notice that there's a very nice pattern to this, and I've done these yellow lines to highlight that pattern. The number 4, for example, is 100. The number 8 in hexadecimal is 1000. The number 10 is 10,000. The number 20 is 100,000. So it just works out to be all round numbers. It corresponds very nicely with the hexadecimal and binary. They just correspond very nicely, and very often in computer systems, if you want to if you store your numbers or digits or characters as binary, well, to reference all those locations in your computer's memory, you can use a hexadecimal address, as they call it. So you can refer to it with using these numbers, and it corresponds very nicely in the two number systems. So that's what hexadecimal is used for. So if you go down to another few here, for example, the next one, 40, again, is another perfect round number. It's what's that? That's a million at this stage? Is it? Yeah, it's so it's 1 and 6 zeros in binary, corresponds to 40 in hexadecimal. So that's it. That's our lesson on number systems. So we discussed all the main number systems that are useful in computers: decimal, octal, binary, and hexadecimal. And then we also saw how that corresponded to computer switches, which is the hardware, as it's called, the actual physical structure that stores these numbers. And then we saw also how that corresponded to an ASCII code. There's a code you for each letter or number or character you might use on your keyboard, which corresponds to a binary number or a specific configuration of switches. That's the end of this lesson on number systems.